Hello, class. In review, remember when we want to do an SN2 reaction, what do we need? We need a primary or secondary alkyl halide and a strong nucleophile. Or if we wanted to do an E2 reaction, we would need an alkyl halide. It could be 1, 2, or 3, but we need a strong base. Let's now take a look at a situation where you have an alkyl halide, okay, and in this particular case, a tertiary alkyl halide, and you treat it with a solvent. All right, let's use the solvent ethanol. And the feature of this solvent is that you can see that it's neutral, right? So this is ethanol. And this solvent is a weak nucleophile and a weak base. And also this solvent is polar. So when you have an alkyl halide, and more particularly a tertiary or a secondary alkyl halide, and you treat it with a polar solvent that is a weak base and a weak nucleophile, you are going to get a mixture of products. You are going to get the product that looks like this. Now, what type of reaction is that? That is a substitution, right? The alkyl halide has been replaced with the ethoxide piece right here. So you can see here's this oxygen right here. It's no longer here. And we'll talk about that in a minute. But overall, you can see that the bromide has been replaced with this piece. And this piece right here came from the solvent. And you are going to get something that looks like that. You're going to have the elimination product. So we have a substitution product and an elimination product. But they go by a different mechanism than the SN2 and the E2. And we've discussed that briefly. That would be an SN1 product, and this would be a E1 product. And I'm going to go through the mechanism to show you what that is. Another thing, okay, so how does this come to be? How does this happen? The mechanism is going to help us figure this out. So if I take and let's do the substitution problem first here. So if we have ourselves our alkyl halide like that, the first step in an SN1 mechanism is the heterolysis step, where the alkyl halide leaves. And then we are left with a tertiary carbocation plus our bromide that fell off. And then in the next step, we're going to have our ethanol like this. And the ethanol is a weak nucleophile, and it's going to come in and attack the carbocation. And then, so we are now going to have something that looks like this. Our oxygen atom attacked the carbon. And so that's what I'm showing here. Do you see how the oxygen atom attacked the carbon of interest? And if we want to star the carbon of interest, I'll do that. You see it's right there. But what is still attached to this oxygen atom? The hydrogen's still there. Did I draw an arrow anywhere showing that hydrogen-oxygen bond broke? No, I didn't. The hydrogen is still there. And there's still a lone pair. This lone pair right there was used to form this bond, oxygen-carbon bond. So now what has happened to the formal charge of this molecule? We have an oxygen atom with 3 bonds and a lone pair, so that makes that positively charged. And then we have one more step. Okay. Now remember, in this reaction here, ethanol is the solvent as well. Okay, so there's going to be excess amounts of ethanol. large amounts in compared to our alkyl halide. So what we're going to have is an excess amount of ethanol, and we said ethanol is also a weak base. So that ethanol, another ethanol molecule, can act as the weak base to do this proton transfer. So this step right here is called the proton transfer step because we are transferring a proton. And so our product is going to be that. Plus, what's going to happen to our ethanol? It's going to add a proton. So now we have a protonated ethanol molecule. But you can see this right here matches this product right there. So that's our SN1 mechanism. Okay. Now let's kind of block this off here. Let's see if I have enough board space, okay, to do the E1 mechanism down here. Let's give it a shot, see what happens here. So in a E1 mechanism, the first step is the same as the SN1. The alkyl halide needs to leave. And we are going to generate a carbocation plus our bromide. The next step is where we're going to take ethanol, which we've already seen right here, acts as a weak base. Can take a look at this carbocation, and the carbocation is on that central carbon, right? So we'll call that alpha. And the beta carbons, there's 3 beta carbons here, has what? A hydrogen atom. And so ethanol can come in now and act as a weak base and grab that proton, break the carbon-hydrogen bond, bringing those electrons there. And what's that going to do? That is going to generate our alkene plus protonated ethanol, which that would have to have what? A positive charge. Now, what's one driving force for this process to happen? Well, look, we have a carbocation. That's not very stable. It wants to react to get to a more stable form. And the more stable form here is the alkene. For one reason, it's neutral. There's no formal charge of +1. And neutral molecules are typically lower in energy and more stable. So what we have here is our E1 product, as you can see here. They match. Now what's interesting, another interesting thing about these two reactions is when you look at the rate. Okay, so the rate for a E1 mechanism and an SN1, they all are dependent on the substrate. All right, the substrate concentration. I'm trying to say a word and spell the other word, and that just did not work for me. Substrate. Now, what do I mean by the substrate? The substrate is the alkyl halide. So if you don't like using the word substrate to refer to the alkyl halide, you could just say alkyl halide if you'd like. But the text refers to the alkyl halide as substrate. So when they were doing the kinetic studies for SN1 and E1 reactions, they would look at this reaction scheme here, and if we just did the same analysis as we did with the SN2 and E2, what you'll notice is that this species right here, if they doubled this concentration, nothing happened to the rate. The rate did not adjust or change. But if they increase the concentration of the substrate, or the alkyl halide. If you double, let's say we doubled the concentration of the alkyl halide, then the rate of the reaction increased by double. So since E1 and SN1, the rate is only dependent upon the alkyl halide, that is going to be a first order reaction. All right. So E1 and SN1 reactions are first order. The rates are only dependent on the substrate. SN2 and E2 is a second order reaction where it's dependent upon the nucleophile or the base and the substrate concentration. Okay. The next thing that I want to do is look at the SN1 mechanism in a diagram. Now, so I've written up the mechanism for the SN1 mechanism again up top. Yes, the arrows have been cut off a little bit. So you see the arrows here cut off, and it's just a little funky. But you've seen the mechanism just a few moments ago, and now I've rewritten it. So what we want to do is take a look at this energetically. So if we draw ourselves a diagram here, on the y-axis we have potential energy right there, and then the reaction coordinate. So we're going to track the energy of this reaction. Okay? So I dropped my pen. I need to go get it. So what we're going to have is our starting material, or okay, that starting point right there is our alkyl halide. So I'm going to just number it right there. So that's going to be our alkyl halide. And what's the first step? It is a heterolysis step. And that takes some energy in order to do that. And so it's going, if this is the alkyl halide, in order to break that bromine carbon bond, it's going to take some energy to do that. Right? And then what happens after it breaks? It turns into, let's make this go down a little bit deeper so we can see some contrast. We'll go down a little bit. Okay. So what do we have here? This right here at the very top, right there, that's the transition state. And down right here at the well, that is the intermediate. The carbocation is what's called an intermediate because after the heterolysis step, there's a moment in time where you create this. And so if we number that, this molecule is going to be right here. The carbocation is an intermediate. This right here is the transition state for this process right here. All right. And then what happens? We have another step. So from 1 to 2, we have the heterolysis step. Then now we have another step here indicated by this arrow where we have a coordination step where the ethanol comes in and attacks the carbocation. So it's going to be there. So what do we have now? Okay. That's not the smoothest looking line. What do we have here? There's the transition state for the reaction of the carbocation with the ethanol to form this species. So that's molecule 3, shown right there. So from molecule 2 to molecule 3, that's the transition state. So from 2 to 3, that's the transition state. And then from 1 to 2 is another transition state. Number 3 here is another intermediate. You see how we have another well right there? And this reaction coordinate's not big enough, so we need to keep going. And then what happens next? We have a proton transfer step. And proton transfer steps are very low in energy. That doesn't take very much. So that is another step. So that's the transition state from 3 to 4. And then right here is going to be our product. And that's our product. So what we have going on here is you can track the energy of the mechanism or the reaction. You see we do so this part right here would be our heterolysis step from here to here. And then from here to here is our coordination step. And then from here to here is our proton transfer. Now, do you recall that I said that the rate of an SN1 mechanism is related to the concentration of our substrate? Right? So when we look at this, so it's only dependent on the concentration of this species. And the reason why that's the case is because it is the rate determining step. Do you remember that from general chemistry? Rate determining step. When you look at an energy diagram, in order to find the rate determining step, you just need to find the hill that's the tallest. And right here we see that that is clearly higher in energy than that peak. Or saying in another way, it is the highest peak. So that is our rate determining step. Okay, so for this example, whenever you find something with the tallest peak, that's the rate determining step. Now, there's some minor exceptions, or there's an exception to that I'm going to show to you in a minute. But I just need to make sure, before I erase this, there's nothing else that I need to say about this. So when we take a look at these two graphs here, it's the same idea. We have potential energy on our y, and then we have our reaction coordinate on the x-axis. So when you look at this graph here, you need to be able to identify a few things. Where are the starting materials? That would be the starting materials. Where's the products? There's our products. Where's the transition states? Well, there's one transition state, and there's a second transition state. Where's the intermediates? It's going to be the well, so that's the intermediates. Which is the rate determining step? Rate determining step. Remember how I said that it's the tallest peak? So the rate determining step would be this one. And what step is that? Well, look, count how many transition states there are. This would be step 1, and this is the second transition state, so that would be step 2. So it is step 2 that is the rate determining step because it has the tallest peak. But then you could encounter an energy diagram like this. Where here's our starting materials, there's our products, there's two transition states. That would be step 1. You can't see that stuff, can you? This is step 2, right over there. So this is step 1 right here. What do we have? We have an intermediate right there. So where is the rate determining step? Where is that? Well, you can see that both of these transition states, they're at the same energy level. And you may argue that they're not. My intent was to draw these transition states at the same energy level, okay? So which one would you select as the rate determining step? Well, you can't use using this logic over here, right? Since they're the same, what you have to do is look for the energy of activation. So, energy of activation. And that is when you compare the steps. So if the first step starts here, and it takes that much of energy to get it going. I'm going to do a lowercase a. But then from the for the second step starts right here at the intermediate going to the product. So what is the energy of activation for the second step? Well, it's going to be from this point to there. So when you have a situation like this, what is the rate determining step? It's the one with the largest energy of activation. So the rate determining step would be step 1. So that's another thing that you could draw over here on this diagram here, is that you have energy of activation as well right there, and that distance right there. So that's the energy of activation for the first step, energy activation for the second step, and the same thing over here. Okay? So when you have hills and valleys, the tallest one is going to be the rate determining step. Unless you come to a situation where all the hills are at the same energy level. And so you have to look at the energy of activation to make that call. Okay? So next, let's look at the E1 mechanism and look at it on an energy diagram here, okay? So I drew the E1 mechanism all over again, showing the steps here. So the first step in an E1 is just the same as this in an SN1, in which our product right here goes through a high energy transition state to get to a intermediate. So if that's R1, that's 1. Here's our transition state for step 1. So that's step 1 right there. There's a transition state. This is our intermediate, the carbocation. So that could be molecule 2. So the intermediate is just the carbocation. We then do a electrophile elimination step, which isn't as hard. And then we go to our product. So so that's 2, which is our intermediate. So we have to make sure we understand that's our intermediate. And then this is step 3. Step 3, no, not step 3. That's step 2. So this right here, the reacting with the electrophile here, that's the transition state. And that is molecule 3, so that's 3 there. So this is step 2. So where's the rate determining step? Well, this peak is taller than that peak. So the step 1 is the rate determining step. And like I said already, the rate is dependent only upon the concentration of the substrate or the alkyl halide, okay? And that's because it has the tallest peak. But in this particular case, look at it, it also has the largest energy of activation. So it has 2 things going for us. Energy of activation is the tallest or the largest, and it's the tallest transition state. Okay. But remember, you only really need to compare the energy of activation to determine the rate determining step if the transition state peaks are at the same level. But since we have the tallest peak here, that wins. That's our rate determining step. Okay. So there's our energy diagram there. What else do we have to say about this one right here? So when you look at an energy diagram here, I want you to be able to say, hey, this right here is the heterolysis step. This right here is the electrophile elimination step. And identify every component of the reaction diagram. So I forgot to put here that this is the same as everything that we've been seeing, potential energy. And then this would be the reaction coordinate. Okay? So let's take a look at this secondary alkyl halide here. And we're going to treat it with water. So when we look at water, water has no charge on it. So we can look at it and say, hey, that's going to be a weak nucleophile or a weak base. It could behave as much. So when the reacting species, so this can react as a base or a nucleophile, and we've identified it as a weak one. But when that attacking species is also the solvent, that has a special name called Solvolysis. So Solvolysis is simply the name for when the attacking species is the solvent itself. So here we have a Solvolysis reaction. But what is the product going to be? I'm going to show you this product. It's going to be this. So what type of reaction have we done? Well, we've done a substitution reaction because we've replaced this bromine with the OH. Now, where did that OH come from? Well, it came from water. Well, how did it come from water? So if we take a look at a mechanism, let's invoke an SN2 mechanism, okay, to kind of understand what's going on here. I could possibly say we have water here, and I could say SN2. Okay, so that means it attacks, backside attack, kicks that off all in one step, and then I'm going to get this. The oxygen attacked that carbon, and it still has the two hydrogens attached, right? I did not remove those, and it still has a lone pair, and it's going to have a positive charge. So then I could do a proton transfer reaction in which I can take water again because it's the solvent. There's a lot of it that can come in, grab that proton, do that to give us our product right there. Now, at first, I'm feeling pretty good about myself. I'm like, hey, this to this. How did that happen? I proposed a mechanism, right? And all the arrow pushing looks good. But guess what? I'm going to throw a wrench in that right here because guess what? When you do the Solvolysis reaction, you also get this product. Let's see here. How do I want to draw it? Like this. Yeah. So do you see? Whoa, whoa, whoa. What have we done here? If we number the carbons, 1, 2, 3, 4. What do we see over here? 1, 2, 3, 4. So that makes sense. The bromine was attached to carbon 3, so that's where you do the substitution. But here, 1, 2, 3, 4, you see how Carbon 3 no longer has the bromine or the OH, but the OH is now over here. So if this is what's happening, these are the products that we're going to get, the mechanism doesn't align with the products. Because if this reaction proceeded via an SN2, and you follow it here, the only product that you can get is this one. Product, we'll call it product A versus product B. The mechanism says you would only get A, but we are getting B. So that tells us the mechanism is wrong. So if we take a look at a different mechanism, maybe we can figure out what's going on here. So let's look at a SN1. So what if we had a SN1 mechanism? So what's the first step? That would be heterolysis step. So that will give us what? That will give us a secondary carbocation. And then what's the next step here? We have water here. So now that can do a coordination step. Attack there. We can see everything still. Good. Can't forget all our carbons. Okay. And then we would then do a proton transfer where we would take another molecule of water and we would do our proton transfer step to give us our product. Okay, so that gives us our product A. So that looks legit. But then how can we have product B form? How is this a correct mechanism? Well, it all comes down to this intermediate right here. That intermediate is key. Because what have we learned in the previous chapter? We've learned about hydride shifts. Right? So look at what can happen here is I'm now going to erase the last part of this mechanism. Okay? So I'm just going to start over here. So I already showed you how to get A, but now that is way too long. I don't like that. Okay, let's see here. You know, I am just messing this up. Let's see, it's like this. Boom, boom. There we go. So what we could do also is do a hydride shift. So I see that on the adjacent carbon from the carbocation, I have a hydrogen. So I could take that hydrogen and do a shift. You see how I'm drawing it from the center of the bond there? And if I do that hydride shift, I'm going to generate this. I'm going to add the hydrogen there. Now the carbocation disappears, but where does it reappear? It is now going to be on this carbon. So why would this do this? Because we went from a secondary carbocation to a tertiary carbocation. And we've learned that tertiary carbocations are more stable. So whenever you generate a carbocation, it is a good rule of thumb to look for rearrangements. And so we have our hydride shift or hydride rearrangement. And now we can have our water come in and attack. And so that would be our coordination step. So that would give us this. That hydrogen's not visible, so I'm going to violate geometry rules so you can see the hydrogen. And then you can see we will do a proton transfer mechanism with some excess water. And so that excess water will come and grab that proton to give us our product. And that matches product B. Right? So what's cool about this reaction right here, because we know for a fact that we get two different products, it supports that there is such thing as an SN1 mechanism. It supports the generation of this carbocation intermediate. If it wasn't for this hydride shift step right here, we would never form product B. And that is one reason why an SN2 mechanism is totally out of consideration, because if it was SN2, we would only get this. But another thing that kind of alerts you to the fact that this can't be SN2 is the fact that this is a weak nucleophile. And in SN2 and E2 mechanisms, it has to be a strong nucleophile or base in order for it to work. Right? So let's look, I'll erase this and then we will look at another type of shift. Now here is an example of another secondary alkyl halide, and it's going to give us two different products. But look at what's happened here. We see that the bromine has been substituted with an OH. Okay, that's a simple substitution reaction. But then when you look at this other product on the right, look at what it's been replaced with. It's been replaced with a methyl group. How does that happen? Well, the mechanism helps us to answer that question. So in order to get two different products here, we have to invoke the first step as the heterolysis step in order to generate a carbocation. And what type of carbocation did I generate? That's a secondary carbocation. So that's stable, but can it get more stable? And that's what you always have to look for. And so what you do is you look at the adjacent carbons and you see if there's a hydrogen. Okay, so if I look at this carbon right here, I see that there's a hydrogen adjacent to the carbocation. So I'm like, hey, that could work. So I'm like, hey, let's try it. So let's just do it. So hydride shift, boom. So what's that going to give me? I'll put the new hydrogen there. Then that generates what? That generates a primary carbocation. So that's not going to work. It's not a bad idea to try it because you're always looking at the adjacent hydrogens. And there it is. When you hydride shift it, what does it do? It gives you a primary carbocation. So that's not going to work. It's not going to happen. But it was a good try. Good analysis. Okay, so that's not going to happen. So what if I looked at the other adjacent carbon? So here's our carbon, adjacent to it's right here. And I'm like, are there any hydrogens? There's not. But remember, if they're methyl groups, you can have a methyl shift. So this methyl right here, or this one, it doesn't matter. Just one of the methyls can shift over. And when that shifts over, it's going to shift like that. We will generate our carbocation. Now, was that a good investment of our time? Yeah, because we went from a secondary to what? A tertiary carbocation. And so that will work. And so we just do the next two steps where we take water and attack in and then do the proton transfer. We will generate that product right there. So one key takeaway that you have to always remember, whenever you generate a carbocation, can you do rearrangements to get a more stable carbocation? Secondary versus tertiary. Tertiary, definitely the stronger or the more stable and more favorable carbocation. Okay, class, now it's your turn to put all these ideas together that we've been discussing to see if you fully understand what's happening here. So here's a reaction that I put on the board. I'm going to tell you that it is a SN1 reaction. Which one of these products is the correct product? There's only one. So which is the correct and only product? And once you figured that out, you always have to explain why. So like if this was a multiple choice question, it's just a flip the coin. If you did not know, it would just flip a coin and that one, right? That's not going to do you much good on my exams. Because for every choice that you make, you have to rationalize and justify why you did that. So this question could be something more like a free response, where it says, which is the major product, or which is the only product, why? And you have to explain your reasoning. So if you just picked the correct answer because you flipped a coin, but had no explanation, you are going to lose the majority of the points. So I would definitely pause the video now and try to figure this one out on your own, and then come back to the video to see what happens. So if we come back here, I told you it's an SN1 mechanism. So we have to do it. So if we do an SN1 mechanism here, the first step is to get that guy to leave, right? So that's going to give us what? That's going to give us a primary carbocation. But how is that even possible? Because we said we don't generate primary carbocations when we do this, right? It does not happen. So if we know that does not happen, then we have to invoke just a slightly different mechanism here. And that's where you do the methyl shift and the heterolysis step all in the same step. So that would be taking this methyl group right here and shifting it to that carbon at the same time the halogen leaves. And so that's going to give us this species right here. Because we know we cannot generate primary carbocations. And now we can then add our water here and then do a proton transfer step to get us to our product. So if that attacks there, never do that. That's a bad idea. Never draw through the bonds. That's a bad idea. All right. If you find yourself with a crazy pathway to get there, you can maybe go like this. Okay. There. Now from there, can you see what the product is going to be? Product B is going to be the only product formed when you do this reaction. All right. That is, I'm putting a stipulation on this, though. I'm saying, hey, this is an SN1 mechanism. All right. Now, could you get to this product via a different mechanism? You could, if you invoked an SN2 mechanism. If you invoke an SN2 mechanism, then you would generate this product. But remember, with an SN2, you have to use a strong nucleophile. If you did that reaction, then you would start seeing A as your major product here. But then again, I'm not going to say we're going to see a lot of this product. Why? Because remember from SN2 material that when you look at the beta carbon, if the beta carbon's very sterically hindered, then an SN2 mechanism is going to be very difficult. Remember that? How to put it all together here. All right. So I take a look at these 4 different alkyl halides. And if I'm going to take each one of these and do the same reaction, treat them with water, okay, to generate our final product as this, okay, or this. Okay. So I'm invoking a E1 or an SN1 mechanism. Which one's going to react the fastest if I have a fluorine or an iodine? Okay. And the answer is, as you go down right here, this is going to be the slow end. This is going to be the fast. So if you have an alkyl halide with an iodine, it's going to react the fastest. Whereas when you have a fluorine, it is so slow that it's totally impractical that we basically say that there's no reaction when we have fluorine. It's really just these 3 right here that we use for alkyl halides to do E1 or to do our reactions with when we're talking about E1 and SN1. Now, why is this the case? Well, it all comes down to this idea of leaving group ability. And we've discussed that before. When you just look at the leaving group of ability, so that's just like this, right? Fluorine doesn't leave very well. Iodine leaves very well. And we rationalize this due to the fact that when it leaves, the fluorine then becomes a fluoride, and then iodine. And when we compare these two, which one's the most stable anion? And when we go down a group, it is about size and polarizability. This is larger, more polarizable, more stable. So this iodine, when it kicks off the alkyl halide, it's chill. It's okay being by itself. The fluoride ion is like, I hate this. I need to be attached to the alkyl halide. So it never wants to leave. Another way we've looked at this is if we look at the iodide and then look at it in water. Which ones? Then it's going to generate our hydronium plus our iodine, right? And if you compare that to if you did hydrofluoric acid and water, you would get H3O plus our fluoride, right? And we just ask ourselves, which one's the stronger acid? And we clearly know this is the stronger acid. And so it's the strongest acid, which makes this a very weak base. And in this context, a very, very good leaving group. So stronger the acid means its conjugate base is the better leaving group. That's another way of looking at it and remembering it. When looking at SN1 and E1 reactions, let's take a look at what type of substrates can work for these reactions. Well, we definitely want a tertiary alkyl halide. That is the best one that will work. Secondary alkyl halides can also work, but we don't see, they're a little bit more rare, but they can still happen. Primary alkyl halides, no way. Why won't that work? Because they generate a primary carbocation, and that's not possible. Okay. But there is not, it's really not an exception, but if we take a molecule that looks like this, Okay, like that, okay? And I put a carbocation right there. How many people would say, no way, we can't form that? And how many of you would say that can't form because that's a primary carbocation? And you would be right based off of this definition, but we don't call that a primary carbocation. When you have a carbon that's a cation directly attached to a benzene ring, we call that a benzylic carbocation. And benzylic carbocations, even though they look like they're primary, they're not. They're benzylic carbocations, and they are stable. And why do you think they're going to be stable? Maybe if I draw something like this. You see the resonance structure? It's resonance stabilized. That's why that carbocation is stable. What's another one? We have something called an allylic cation. Let's see if I spelt that right. So we have an allylic carbocation, which looks like this. When you take a first look at it, you're like, that can't form, no way. That's a primary carbocation. It's not. It is a allylic carbocation. And why is that stable? Why does that form? Because, as you can guess, we have a resonance structure. And due to resonance, that's going to stabilize this allylic carbocation enough that it can form. And so you can have a reaction with these two types of carbocations. So for example, if you had a reaction like this, let's see here. H2O, okay. Can that undergo an SN1? Yes, it can. We'll keep consistent here. That is very plausible. Okay. Okay. Let's see. What's another thing that we need to talk about? I know we're a little bit over, but I want to say one more thing, teach one more principle, then we will conclude this video. All right. That is, can you have this happen? All right, and we have a halogen there. Remember, that carbon that the halogen is attached to is sp2 hybridized. Can this process happen? Can the halogen act as a good leaving group and leave? And generate this? No, it cannot. It cannot happen. All right? And the reason why it cannot happen is because this carbocation that we're proposing is so unstable. And the reason why it's so unstable is due to the fact to effective electronegativity. Effective electronegativity. Yeah. Okay, so that does not happen. And if you need to review effective electronegativity, that's the reason why that doesn't form. And so the same reason this does not happen. Okay? Look at this one. Put a halogen right there, right on the benzene ring. Okay? Can this happen? No, it cannot. Okay? That cannot happen because why? We have a sp2 hybridized carbon. And the reason why? Same idea, effective electronegativity. Okay, so that's where we'll end on this video.